All right, so today we are going to be looking at a really important geometric quantity that we can measure about a curve. And I'm speaking about the curvature of the curve. So we'll be talking about what is curvature of a parametrized curve, how do we measure it, and so on and so on. First, an intuitive understanding of what the curvature is supposed to be. The curvature is supposed to be a function, first of all, so it will be the curvature function, and it will measure at any given time t just how curvy our curve is. And so what do I mean by that? Well, it's a little loose at the moment, but in essence, if I have a parametrized curve, and maybe here's the locus of the parametrized curve, then I want a function that will measure at any given point just how curvy the curve is. So at certain points, like maybe this point and this point and this point, we might expect to be high curvature, right? That seems to be points where our curve is very curvy. And so we might expect our curvature function to reflect that somehow. Maybe our curvature function is a large number at those points. While other points, like maybe this point right here, or this point here, this point here, those are points of considerably lower curvature, right? The curve seems to be curving much less there. And so we might expect our curvature function to have a smaller number at those points. So intuitively, that is what we mean when we discuss a curvature function. We want it to be a function that measures how curvy our curve is. And we need to keep that in mind because when we get to the actual definition of curvature, we'll see that the actual definition is a little bit more complicated than that. So here's our actual definition of curvature, right? So first we have to start with a parametrized curve. It's going to be, or we're going to assume that it's a C2 curve, which means that we can take at least two derivatives of it and be okay, and have those, up to second derivative, the derivatives are continuous. So it's a C2 curve. It's a regular curve, which means that the first derivative is never equal to 0. And so if we have that as our base, a C2 regular curve, then the curvature function, which we will denote using a kappa, so this is going to be kappa sub g of t, but I'll usually just say out loud kappa of t or k of t or the curvature function, but formally it's kappa sub g, is the unique function that satisfies this equation. So kappa is the unique function such that the derivative of the unit tangent vector, right, t prime, is equal to s prime times kappa times u. And just to remember what all these objects are, like we said, this is the derivative of the unit tangent vector. This is the derivative of the arc length parameter s. And what we saw in a previous video was that s prime is going to equal the speed of the parametrized curve. So this is the speed times kappa times the unit tangent vector. And so what we're claiming is that there is a unique function such that at any given time t, this equality will hold. And kappa is determined using that expression. It's determined to make this equality hold. So wow, that is a weird definition, right? Like that doesn't seem anything like our intuitive definition. And we should really be a little careful here, right? There are a lot of big questions that come with this definition. For example, we claim that kappa is the unique function that satisfies this. So, bare bones, important question to ask, does such a function even exist? And if it does exist, is it necessarily unique? Is there a unique function that always works here? Other important questions we can ask include, let me actually just skip ahead here, issues with this definition, right? Does such a function exist? Is this function unique? Very unclear right now. Number 3, how do we find such a function? Right? Notice this function is defined implicitly. We're just saying that it exists such that it's the unique function that makes this hold true. Okay, if we eventually determine that this is a good function and it is unique, can we write it explicitly, find a formula for it? Excellent question. Unclear. Is this measurement invariant under reparameterizations? Always an important question to ask, right? It seems like if we're measuring how curvy the curve is, and I already did this a little bit, I was pointing to individual points on the locus of this curve with no regard for which parameterization I was using. So theoretically, if this is a property of the locus, of the underlying curve, then it should be invariant under reparameterizations. I should get the same reading regardless of which parameterization I am using. So is that the case? Totally unclear. Not sure at this moment in time. So yeah, is this invariant under reparameterizations? We hope so, but we should confirm. And finally, so important, does this weird definition actually measure how curvy the curve is? Totally unclear at this moment in time. So let's get into this. And I'm going to start with these first two bullet points. Does this function exist and is it unique? It turns out the answer is yes, it does exist and it is unique, but that's not really that easy to see. And in particular, I want to caution you that when I go back to this equation, let's find the equation. When I go back to this equation is a vector-valued equation, right? This left-hand side is a vector. This right-hand side is a scalar times a vector. So this expression is vector-valued. This expression is vector-valued. And so I'm claiming that these two vectors at time t are equal to each other. And so in particular, I might want to make sure, for example, that they even can be equal to each other, that when I take the derivative of t, it will point in the same direction as u, right? If they're pointing in two different directions, they won't be the same vector. We'll be completely in trouble. So let's take a look at this. In order to begin answering these first two questions about existence and uniqueness, it is worthwhile, whoa, sorry team, let's not look over there. It is totally, maybe we fade in here. It is totally worthwhile to make sure that, in fact, t prime points in the same direction as u. And we can do this by seeing that t prime is actually perpendicular to t. And here's a clever trick to show this. I'm going to use this symbol to denote perpendicularity, right? So I'm just claiming now that t prime, let's get this right, t prime is perpendicular to t. Now to do this, right, the clever trick relies on the observation that the length of t, the unit tangent vector, is 1, right? It has unit length. And so therefore, the length squared is just equal to 1 squared, which is just 1. And because this is a function of time, right, every single time gives us a new unit tangent vector of length 1, it turns out that the t derivative of this quantity is just the t derivative of the constant function 1, which is 0. All right, so far so good. But it turns out, right, this is useful to us because this expression, norm of t squared, is really just t dotted with t, right? Which is what we, this is how we originally defined length. And so what that tells us is that the derivative of this quantity is really equal to 0. And so let's take a look and see what that is, right? So what we now know is that 0 is equal to the t derivative of the expression t dot t. But we know from taking derivatives of dot products that this is going to really equal, right? There's a product rule at play here. This will become t prime dotted with t, right? That's the derivative of this first piece dotted with the second, plus the first piece dotted with the derivative of the second. So we get these are equal to each other, right? But then that's just 2 times t dotted with t prime. And so what we've really shown is that t dot t prime is equal to 0. And if t dot t prime is equal to 0, that means that t is actually perpendicular to t by properties of dot products, right? The angle between t and t prime is pi over 2, and so they're perpendicular to each other. Now, what does that mean for us? Well, since t prime is perpendicular to t, this means, at least in R2, that t prime has to be a scalar multiple of u. And let's take a look at that, right? Let's confirm that. So here's a given curve. Here's my unit tangent vector, and here's my unit normal vector with that pi over 2 rotation. T prime, we just said, has to be perpendicular to t. And so no matter how I draw it, let me choose a new color here to draw this in. Right? No matter how I draw it, it will necessarily be perpendicular to t. So pointing either up here or down here. And if we were to look at an explicit example and crunch the numbers, we would probably see that t prime would point maybe in this direction. So it's perpendicular to t, and because t and u are perpendicular to each other, t prime is necessarily a scalar multiple of u. In this case, a negative scalar multiple of u. So it turns out that that is actually enough for us to get not only existence, but also uniqueness of the curvature function. And here's why, right? If t prime is a scalar multiple of u, let's go back 2 slides here. Right? If t prime is a scalar multiple of u, then this piece is a scalar multiple of this piece, and the scale, right, the scalar that we need to multiply by, can be determined just using s prime and kappa. So, because s prime will not equal 0, because our x is regular, we can uniquely determine what kappa should be in order to make this equation actually hold. So, turns out, does this function exist? Yes. Is this function unique? Yes. How do we find such a function? Ooh, okay, that's a little bit trickier. It turns out that there is a formula for how to calculate curvature. It will just be a little bit hard for us to rigorously prove is correct at this moment in time. Specifically, we need properties of vectors in 3-dimensional space, and we need cross products to help us with this proof, which we won't get into in this video. So it turns out, so here I'm going to call it an awesome fact, although this is totally something that with a Calc 3 background we can easily prove, that if our parametrized curve is given by x of t comma y of t, then the curvature function is given by this slightly complicated looking formula. Specifically, we need the first derivative of x times the second derivative of y minus the first derivative of y times the second derivative of x, all divided by x prime squared plus y prime squared, collectively raised to the 3/2 power. Right? Like I said, I think this is something we could absolutely prove, but we won't be doing that in this video. We'll simply call it an awesome fact. Now, with this awesome fact, though, we can say, yes, we have found, yes, we have found such a function. And it, is a little bit complicated to compute, but we can do that. These last 2 questions I'm going to momentarily pause on answering. It turns out, yes, it is invariant under reparameterizations, and yes, it measures what we want to. But we'll talk about that in a moment. First, just to talk through a explicit example, right? Here's a function, a parameterized curve, x of t equals t comma t squared. Let's say parameterized between -1 and 1. I might ask, what is the curvature function of this curve, and where is its curvature function at a maximum? Where does it get as curvy as possible? We might have an intuitive guess based on the picture, but let's crunch some numbers and see that it actually becomes what we want it to. So since this is our function, right, this means that our x of t is just equal to t, our y of t is equal to t squared. And so when it comes time to compute our curvature function, remember, I'll write this up here. Our curvature function was x prime y double prime minus y prime x double prime over x prime squared plus y prime squared to the 3/2. right? So what we need to do is calculate x prime, x double prime, y double prime. And luckily in this case, it's not so bad, right? We'll end up getting, that x prime is just equal to 1, x double prime is equal to 0. We'll similarly get that y prime is equal to 2t, y double prime is equal to 2. And so our curvature function, right, will equal x prime times y double prime, that'll just be 2, minus y prime times x double prime, ooh, that's going to be 0. So 2 minus 0 over x prime squared plus y prime squared all of that raised to the 3/2. And I think maybe the easiest way we can write this is 2 over 1 plus 4t squared raised to the 3/2. And we'll leave it like that. Cool. So that's sort of a messy function, but it does give us a measurement at each point in time t for what the curvature should be at t. And in particular, in this case, even though this is a complicated expression, right, and it is sort of a complicated expression, we can still see where the curvature achieves its maximum. And it'll happen at t equals 0, because any other value of t will only increase the denominator, which will in turn shrink the entire size of the fraction. So this denominator is smallest, and therefore the curvature is largest, specifically at t equals 0. And so the perhaps not surprising observation is that on this parabola, the curviest point of the parabola, the point where it's curving the most, occurs right here at time 0 at the vertex. So kind of a cool example. Okay, so I want to end by talking about parameterizations and reparameterizations. I should first, I guess, go back and answer this question 4, at least in a slightly hand-wavy way. It turns out that computing curvature will be independent of reparameterizations, and the loose reason why, again, it's slightly hand-wavy, the loose reason why, sorry about that, the loose reason why is because under a reparameterization, we would affect the speed at which our function is being traced out. So we would affect the speed of the parameterization, and we would affect the derivative of the unit tangent vector. We would affect how quickly the unit tangent vector is curving. And it turns out that the reparameterization would affect that and affect the speed in exactly the same way. So each of these two sides of the equation would be affected by the same factor, and the kappa would remain unchanged. So kappa will be invariant under reparameterization. Slightly less hand-wavy, but still a little hand-wavy. Maybe I should say I'll leave the details to any of you all if you're interested. Would be to look at this equation here and see what would happen if we replaced our x of t with a reparameterized curve. Right, so if we had a reparameterization xc of t, which would be x of f of t, so that will be little x of f of t, comma, little y of f of t. There we go. We could see what would happen if we computed the curvature function for xc. And in particular, when we took a lot of these derivatives, the x prime, the y double prime, et cetera, these extra f primes and f double primes might factor or might find their way out of the equation as a result of chain rules. And it is, sort of remarkable, and again, totally within your realm of being able to compute, if you're interested, to see that under all of those chain rules, the extra factors that result, these f primes or potentially f double primes, will nicely cancel out in this equation. So that will factor out, and then the numerator factor will exactly cancel with the denominator factor. So it turns out that under reparameterization, we would end up with the exact same kappa, the exact same curvature. So that's awesome. And though it was a little hand-wavy, I'm going to put a nice check there to say that that's true. Finally, though, we still haven't really verified whether or not this measures what we want it to, and that's important. So let's double check that. So for any parameterization, we have these two defining characteristics of curvature. First, our implicit definition, and then the explicit formula that we computed. So for any parameterization, both of these hold true. My question is, what about a specifically unit speed parameterization? And as a reminder, for a unit speed parameterization, we're often looking at the parameter s. And what made a unit speed parameterization was that the speed, right, which we previously called s prime of t, will now just be the derivative of the variable s, and that's equal to 1. So maybe not that surprising, a unit speed parameterization has speed equal to 1, and so this piece right here will specifically have speed equal to 1 in a unit speed parameterization. Secondly, though, the speed is determined as the norm of the velocity vector, and the velocity vector was x prime comma y prime. So not only is this equal to 1, but the norm of the velocity vector, right? And as a reminder, that would be the square root of x prime squared plus y prime squared. That will also equal 1. And how does that affect us up here? Well, that is exactly the denominator. I should say the denominator is equal to this quantity cubed. So in a unit speed parameterization, this whole thing just becomes 1 cubed, which is 1. So it turns out under a unit speed parameterization, both equations simplify remarkably. And what we get is, for a unit speed parameterization, the curvature is determined implicitly by this formula, and it's determined explicitly by this formula. That entire denominator just became a 1. And this really does answer that final question, especially looking up here, right? What we are now seeing is that the curvature is intrinsically linked to t prime, how quickly our unit tangent vector is changing. And as we've seen, right, if we have an area of high curvature, let's say like this area right here, the unit tangent vector will change very, very rapidly, right? Here's unit tangent vector one moment, here it is the next moment, here it is the moment after that. That unit tangent vector is just whipping around and changing its direction radically. And so in areas of high curvature like this, the derivative of the unit tangent vector will be very large in magnitude, and in return, we'll end up with a high curvature measurement, a large curvature measurement. Whereas here, area where it's really not curving that much, right? Here's the unit tangent vector one moment, here it is the next. It's really not changing much at all. And so in moments where, or in places where our curve is relatively flat, where it's not that curvy, turns out that curvature will be measured very small, very close to 0. And so indeed, curvature does show us how curvy the curve is, even though it wasn't immediately or initially clear that that was the case.